Mechanical wave is a disturbance that travels through some material or substance called medium. Now the question is, do all waves require a medium to travel? The answer is, almost waves require a medium to travel, except this what we call the electromagnetic waves. So what are these electromagnetic waves? So these are the gamma rays, the visible light, the ultraviolet rays, the X-rays, microwave, radio wave, and etc. Now we must remember that medium must be inelastic, we have restoring force, and has inertia which has mass. Now, we have different varieties of mechanical wave. So first, where the medium is a string or a rope under a tension. So if we give the left end of the rope or a string an upward shake or wiggle, the wiggle travels along the string. Another is the medium is a liquid or gas in a tube with a rigid wall at the right end and a movable piston at the left end. So if we give piston a single back and forth motion, the displacement and pressure fluctuation travel down the medium. This time, the direction of the particles of the medium are back and forth along the direction of the wave travel. Next is, the medium is a liquid in a channel, such as water in a ditch or canal. When we move the flat board at the left end forward and back once, a wave travels down the length of the channel. In this case, the displacement of the water have both longitudinal and transverse components. The three different varieties of mechanical wave have their common. First is, they both propagate with a definite speed. This speed of propagation is what we call the wave speed. Second is, they undergo up and down and back and forth motion. Lastly, to set any of the system into motion, we have to put energy by doing mechanical work on the system. Now, what are the types of mechanical wave? So, we have first the longitudinal wave. Longitudinal wave is where the disturbance is parallel to the direction of the wave propagation. Example of this is the longitudinal wave on a fluid, where fluid is placed in a tube with a rigid wall in the right side and a movable piston in the left side. As you move the movable piston back and forth, the wave occurs. As the wave passes, each particle of the fluid moves forward and backward parallel to the motion of the wave itself. Transverse wave, where the disturbance is perpendicular to the direction of the wave propagation. Example of this is the transverse wave on a string. As the wave passes, the particle on a string moves up and down transversely to the motion of the wave itself. We have also waves on the surface of a liquid. So, as you move this flat board back and forth, so the wave occurs. As the wave passes, all particles of the surface of the water move in a circle. We have what we call periodic wave. So periodic wave is when each particle undergo periodic motion as the wave propagates. The shape of the string at any instant is a repeating pattern. So like this one. So it is in one period. In a periodic wave, we have the wavelength, which is in the symbol of lambda, and the amplitude in the symbol of letter A. So, lambda or wavelength is the size of or the length of the wave from crest to crest or trough to trough. So in order to use the relationship between the speed or the wave speed and the wavelength, then the frequency. So wave speed is just equal to wavelength over period. So we learned previously that frequency is equal to 1 over period. So to rewrite, V or wave speed is just equal to wavelength times its frequency. And now this is our periodic wave. So frequency is the property of the entire period. Now we have the periodic transverse wave. Suppose we move the spring up and down with a simple harmonic motion with amplitude A, frequency F, angular frequency which is equal to 2 pi F, and period T 1 over F, or just equal to 2 pi over angular frequency. The example below show one way to do this. In this situation, the wave that result will be a symmetrical sequence of crest and trough. Now we will see that the periodic wave with a simple harmonic motion is easy to analyze, and this is what we call the sinusoidal wave. We can also say that any periodic wave is the combination of the sinusoidal wave. Now we have to be very careful to distinguish between the motion of the transverse waves and the particle of the string. So we have to bear in mind that the wave moves with a constant speed v along the length of the string, while the motion of the particle is simple harmonic and perpendicular to the length of the string. In a periodic wave, the shape of the string at any instant is a repeating pattern. The length of one complete wave is the distance from crest to crest and trough to trough. So this distance is what we call the wavelength, or written in the symbol of lambda. The wave patterns travels with a constant speed v, advances the distance which is the lambda in a time interval of period t. So we can rewrite it as wave speed, which is v, is equal to our wavelength over its period. Because our period t is equal to 1 over its frequency, so now we can rewrite it as wave speed, or v, is equal to lambda times its frequency. So this is now the equation of the periodic wave. Now we have also what we call the periodic longitudinal wave. In order to understand the mechanics of this periodic longitudinal wave, we consider a long tube filled with water or fluid with a movable piston at the left end. If we push the piston in, we compress the fluid near the piston, increasing the pressure in this region. So this region pushes against the other region, and so on. And a wave pulse moves along the tube. Now suppose we move the piston back and forth with a simple harmonic motion. The motion forms a region of fluid, so where the pressure and density is increased or reduced. So we call the increased density as compression, and we call the reduced density as rarefaction. So the wavelength here is from the compression to the next, or to the rarefaction to the next. Now look at the waves on a straight string. So, ignoring the sag of the string due to the gravity, the equilibrium of the string is along straight line. So, taking the x-axis. So, waves on the string are transverse and the wave motion of the particle is along the y. So, the value of y depends on x and on time. So, thus, the y function is both x and t. So, the y function ay di debali. So y is the function of both x and t. So we have y is equal to y is the function of x and t. So we call this function y x t as the wave function. Which describe the waves. So we can use it to find the displacement of a particular at any time. So we can also find the velocity of the wave, acceleration of the wave, shape of the string, and any about the behavior of the wave. Every particle of the spring oscillates with simple harmonic motion with the same amplitude and frequency. Oscillation of particle at different points on a string are not all in step with each other. So we call this difference as phase difference. So for example, if one point has its maximum positive displacement, at the same time, the other has its own maximum negative displacement. Now suppose the displacement of a particle on the left end of the string is 0, so x is equal to 0, where the wave originates. So it looks like this. Now, it will given us the y function of x and time is equal to a cosine angular frequency or W times time. So since angular frequency is equal to 2 pi f of so we can rewrite it as a cosine 2 pi f t. So this is now our equation. So the wave disturbance travels, this is our y, this is our x. So the wave disturbance travels from x or the origin to same point x to the right. So it's positive value in an amount of time given as x, amount of time, x over v. So the motion of the point x at the time t, so the same motion of the point x equals to 0. So at earlier time, so we have t minus x over v. So by the value of time, which is equal to t minus x over v, we can now rewrite the equation as y is the function of x, t is equal to A cosine angular frequency times, so we can replace the time as t minus x over v. Now, because cosine is negative theta, so we can replace the, or we can rewrite the equation as y xt is equal to a cosine so we can again simplify our W, which is our angular frequency, into, so angular frequency, so we all know that angular frequency is equal to 2 pi f. So rewrite the equation into y is function of xt. So now, so this equation will be now our, or what we call the sinusoidal wave, which moving in positive x direction. So we can use this equation if the wave move along the positive x direction. Now the displacement of y and yxt is a function of both location of x and time. So we can rewrite the equation in several useful forms, such as we can express this in period is equal to 1 over its frequency, and wavelength is equals to wave speed over its frequency. So substitute the value. So substitute the value of f as 1 over t, and substitute the value of our v, which is lambda and frequency. So cancel the frequency. So we have now the equation y function of x and time is equal to a cosine 2 pi x over lambda minus time over t, or the period. So this equation is what now we call the sinusoidal wave, which is moving in the positive x direction. We can also define the wave number k, which is equal to 2 pi over lambda. So we will substitute the value of k and f, which is f is equal to omega over 2 pi. So into wavelength frequency relationship form. So the v is equal to lambda times frequency. So this will gives the omega is equal to vk. So this equation now will be our periodic wave. Now we can rewrite again the previous equation using the periodic wave in the angular frequency and the wave number. So we have y in the function of x and t is equal to a cosine. So we have k in the form of wave number. So k x minus omega times time. So this is also the sinusoidal wave. moving still in x or positive x direction. So, graphing the wave function. So, we use the equation y is a function of x and t is equal to a cosine kx minus wt. So, in graph A, so we set the y function of x and t as a function of x as the time is equal to 0. So, this will be the graph. While the graph B is we consider the function y is the function of t as x is equal to 0. Now, if we use this equation to plot y as the function of x and t which is equal to 0, the curve shows the shape of the string at time is equal to 0. So, the graph B, if we use still this equation to plot the y, the curve shows the displacement of the particle at x is equal to 0 as a function of time. So, if we get the equation of the graph A, we can have the equation of A as y is a function of x, where our t is equal to 0. So, we have A cosine kx. For graph B, so we have this equation, y is function of where our x is equal to 0, t. So, we have A cos, so negative wt. So, because cosine negative theta is equal to cosine theta, so we can write this as A cosine wt. So, we can also express this angular frequency into 2 pi f t. Although the graph may look the same, but we will bear in mind that graph A shows the shape of the string at time is equal to 0, and graph B shows the displacement of the particle at the position x is equal to 0 at a function of time. So, for a wave traveling at a negative x direction, so we can have these equations. So, again, we just change the sign negative into positive. So, this will be the equation or sinusoidal wave traveling it at the or moving in negative x direction. Negative x direction. So, we call this quantity as phase. This plays the role of an angular quantity, which is for the value for particular any values of x and time determine what parts of the sinusoidal cycle is occurring at the particular point and time. So, we have for a crest where our y, which is equal to positive amplitude, so we have the phase could be 0, 2 pi, o 4 pi. So, in the situation of trough or in the for a trough, so where our y is equal to negative a or negative amplitude, so the phase could be pi, 3 pi, 5 pi, and so on. So for a wave traveling at x direction, that means that kx minus wt is equal to constant. Is constant. So taking the derivative with respect to t, so we find k dx t, which is equal to w. So or we have dx dt is equal to w over k. So comparing this equation to equation w is equals to vk, so where it is equal to the speed of v of the wave. So because this relationship v sometimes called the phase velocity. Phase velocity. Or phase speed could be the better term. Phase speed. Now we have particle velocity and acceleration of sinusoidal wave. So in order to find the transverse velocity of a particle, we have to take the partial derivative of a wave function, y, function of x and time, with respect to t, keeping x as constant. So we have the equation y is a function of x and time is equal to a cosine kx minus omega t. So get the partial derivative. So since we're going to get the velocity of the particle which is moving along the y axis, so we have vy as a function of x and time, so it's equal to partial derivative of y as a function of x and time, so with respect to partial derivative of time. So derivative of cosine, so we have negative sign, so copy the constant a, kx minus omega t, and then the derivative of this one with respect to time, so we have negative omega, so transfer the negative omega in the side, on the front, so we have negative times negative, so we have positive omega times a, which are amplitude, sine kx minus omega t. So this is now our velocity of the particle on the transverse wave. So omega times a, or the amplitude, is what we call the maximum particle speed. So omega times amplitude, or the maximum particle speed, could be greater than, less than, or equal to the wave speed. So depending on the value of our frequency and amplitude. Derivative. So in order to get the acceleration of the particle, so we have just get the second partial derivative of y as a function of x and t with respect to time. So we have this equation, the wave equation, so we have derivative of cosine, so we have negative sign, so copy this expression, so kx minus omega t, and then derive this one, so we have negative omega, so transfer here, so negative times positive omega, so a sine kx minus omega t, and then so take the second derivative again, so derivative of sine, so we have cosine kx minus omega t, so derivative of this one, so we have negative omega, so transfer the negative omega here, so we have negative omega squared a cosine kx minus omega t. So this will be the equation of the acceleration of the particle, or we can just rewrite it in the simplest form, or we can simplify it into omega squared y is a function of x and t. Since
e cos kx minus yt, or this expression is the expression of y as a function of x and t. Now we can also get the slope of the string. So in order to get the slope of the string, so we have to get the first partial derivative of the function y as a function of x and t. So at this time, with respect to x, and then our time will be the constant. So we have partial derivative of y as a function of x and t with respect to x. So we have, so as the previous, which is our equation, y function of x and t equals kx omega t. So from this equation, so we have derived the function, or we have derived the function with respect to x. So we have, so cosine, so we have negative sign, so kx minus omega t. So since our time is constant, so it is 0, so we have k. So we put the k at the front of the equation. So we can also get the curvature of the string. So in order to get the curvature of the string, so we get the second partial derivative of y as a function of x and t with respect to x. So from this equation, so we have, so still the same with the first derivative. When we get the slope of the string, so again we have to derive, so sine, derivative of sine, so we have cosine. So at this, we have, when we derive this one with respect to x, so we have k, so we have k times k, so we have k squared, so negative k squared a cosine, so kx minus omega t. So this will be the equation on how to get the curvature of the string. So second derivative of y is a function of x and time with respect to time, so is equal to negative omega squared times y as a function of x and time, and second derivative of y is a function of x and time with respect to x, which is equal to negative k squared times y as a function of x and time. So using this relationship, omega is equal to vk, which is v is the wave speed and t is the wave number. So we can say that second derivative of y as a function of x and time with respect to time divided by second derivative of y as a function of x and time with respect to x. So we have omega squared divided by k squared, so which is equivalent to our wave speed. So and second derivative of y is a function of x and time with respect to x, so is equal to 1 over v squared times the second derivative of y as a function of x and time with respect to time. Will be our wave equation. So wave equation. Another view of a wave at time is equal to 0 is this one in the transverse velocity of the particle. So the vector shows the transverse velocity of Vy and transverse acceleration Ay at several points on the string. So from t is equal to 0, so Vy, which is on upward, and our acceleration is going to downward. At x is equal to 0, so we don't have acceleration here. So our acceleration is equal to 0, but we have the velocity which is going to upward, so Vy. And then as our particle 3, which have the velocity y going up and also the acceleration going up. And then another particle, so we have, since this is the maximum height of the particle, so we don't have velocity along y, it's equal to 0, but we have the acceleration which is upward. And then the particle 4, so we have the component Vy, so which is downward, and our acceleration is upward. Then particle 4, which is on the x equal to 0, so we don't have acceleration here, but we have the component velocity which is going downward. And then the particle 5, so we have the same, so it's going down the velocity and the acceleration. And then particle 6, particle 8, so we don't have the velocity along y since it is on the maximum height, so it is 0, but we have the acceleration which is going downward. And then another, so we have particle here, so the acceleration is going downward but our velocity is going upward. And then here, so we don't have the acceleration here since our x is equal to 0, and our Vy which is going to upward. And then last particle, we have the component Vy which is going up, so we have velocity along y is going up and then acceleration along y still going up. That as the time 0.05, so what will be the position of the particle? Since the particle is not moving, but the direction of the particle's movement will be up and down. Black graph is the original, which set as the time is equal to 0, and the red graph will be as the time past 0.05. We set the 1 prime as the position of the particle as time past 0.05. So we have, so this is the starting, so t is equal to 0. So the particle move up, so we have the 1 prime equal to, so move up, which is to 2 prime, so and so on. So go back in here, so the acceleration ay at each point of the string is proportional to the displacement y, that point. So we have to remember that the acceleration is upward when the curve is upward, so just like this one. So when the curve is upward, so our acceleration is going to up, and downward, the acceleration is downward when the curve is going to downward. Light waves on air have much greater speed of propagation than those sound waves. We have the light waves, which is 3 times 10 to the power of 8 meter per second, while the sound waves, we have 344 meter per second. This is the reason why we see the bolt of lightning before we hear the thunderclap. Here we will see what determines the speed of propagation of a particle kind of a wave, which is we consider the transverse wave on a string. The first method, we consider the perfectly flexible string. If figure A, consider the string which is in equilibrium. In the equilibrium position, the tension is labeled as F, and a linear mass density which is mu. When portion of the string are displaced from equilibrium, figure B, that part of the string is in motion while the other is at rest. When portion of the string are displaced from equilibrium, the mu decreases a little, since our mu is mass divided by length, and tension increases a little. So ignore the weight of the string so that when the density is at rest, the equilibrium position is perfectly straight line. So this, you consider this one. So this is the force of the hand. So there is a hand here. So this is a hand here. Starting at T is equal to 0, then apply a constant force, Fy, at the left end of the string. So we might expect that the end would be moved constant, diba? When you lift the string, so move constant, which have a constant acceleration. So that would happen if we apply the force to the point mass M. So there is a point P here, which is our point mass. But the effect of Fy, the applied force, is to set successively more and more mass in motion. Wave travels with a constant speed v. So v is constant. So the division point P, from here point P, between moving and removing portion with the same constant v. So this figure shows that all particles in moving portion of the string move upward. Diba? All particles here move upward. So with constant velocity Vy. So, but not the acceleration, since the acceleration here is constant since you applied a constant force. So there is no change of velocity since acceleration is the change of velocity. So this is because the impulse of the force Fy up to time is, so we have the force F, so up to time, so we have this one. This is the impulse, and according to the impulse momentum theorem, the impulse is equal to the change of total transverse component of momentum. We have mvy. This is the impulse and momentum theorem. The total momentum must increase proportionately with time. But since the position of the point P moves, moves with constant speed, so the length of the string that is in motion, so the total mass M in motion are also proportional to the time that the force has been acting. Change of momentum must be associated entirely with the amount of mass in motion, not increasing amount of Vy, but increasing the mass. So, since we cannot increase the amount of Vy, diba? Because we apply the constant force. Therefore, the amount of moving portion, we increase the mass in motion, but not the amount of Vy. So, at time t, the left end of the string has moved up, up a distance Vyt. So, we have the distance Vyt. At the boundary point has advanced the distance. So, from boundary point P and the distance of the upward force. So, we have the boundary point P, Vt. So, the total force at the left end of the string has components F and Fy. F, because there is no motion in the direction along the length. There is no unbalanced horizontal force. Therefore, F is the magnitude of horizontal component. To derive the expression of a wave speed V, we again apply the impulse theorem to the portion of the string which is moving at a time that is to the left, which is P. So we have Fyt is equals to mvy. We have Fy over F, which is our tension, is equal to Vyt over its Vt. So this is in the relationship on the right triangle on the hand and the right triangle at the vertex point P. So Fy, so get the force along y. So Fy is equal to F Vy over V. And our transverse impulse, so we have Fy T is equal to F Vy over V times time. So the mass of a moving portion of the string is the product of mass per unit length and the length Vt. So this one. This transverse momentum is the product of mass and the transverse velocity Vy. So this is now is what we call the transverse momentum. Note that the momentum increases with that time, not because mass is moving faster, but because more mass is brought into motion. So put the impulse of the force Fy equal to the total change of the momentum of the system. So we can obtain the F is equal to Vy over V times time, which is just equal to mass per unit length times Vt and then the transverse velocity. So in order to solve the wave speed, solve for V, we have V is equal to force over mass per unit length, mu. This is now the speed of the transverse wave on the string. Now we have the second method on solving the wave speed on a string. We have here the alternative derivation of V is equal to F over mu. Now we apply here the Newton's law, which states that summation of force of all forces is equal to mass times its acceleration. Small segment of a string whose the length of the equilibrium portion is change of x, and then the mass of the segment is m is equal to mu times change of x. So the forces at the end of this presented in the terms of their x and y component. Now we have the x component have equal magnitude of F, and then the add to 0 because the motion is transverse and there is no component of the acceleration in x direction. To obtain the F1y and F2y, so we have to take note that F1y divided by F is just equal to partial derivative of y with respect to x. Since the slope of the string at point x signifies the slope of the string, and then F2y over F is equal to the slope at point x times change of x. This equation reminds us that derivatives are evaluated at point x and then point x plus change of x. We find the y component of forces at Fy is equal to F1y plus F2y, which is equal to F times partial derivative of y with respect to x, x plus change of x, minus partial derivative of y with respect to x with the subscript of x. Equate this equation to mass, which is equal to mu times change of x, and then multiply to the acceleration along the y, which is the partial derivative of y with respect to time. So we have F times partial derivative of y with respect to x, subscript x plus change of x minus the partial derivative of y with respect to x with subscript x, which is equal to, so we equate this equation, mu times change of x and then the acceleration along y, which is partial derivative of y with respect to time. And then this equation, we have to divide it by the force times change of x here. So we cancel the f, we have remain the change of x, and then is equal to, so we have mu change partial derivative of y with respect to time, so cancel the change of x, so we remain the f. Now take the limit of change of x into change of x is equal to 0. In this limit, the left side of the equation becomes the derivative of y with respect to x at a constant t. So that is now the second partial derivative of y component with respect to x. So we have the second derivative of y with respect to x is equal to, so this one, and then copy this one. So we have mu, second partial derivative of y with respect to time. As you can see, this is just equal to the wave speed have solved previously, which is this one. Finally get the wave equation in the transverse wave or the string, so which is just equal to v square root of f, which is our tension force, times the speed of the mechanical wave. So from the equation, v is equal to square root of f divided by mu. So this gives the wave speed for only the special case of mechanical wave on a straight string in a rope. Remarkably, it returns to the general form, which including waves on a string that is have the general expression of the wave speed. So which is v is equal to square root of restoring force returning the system to equilibrium divided by inertia resisting the return. The tension F, this is our restoring force, and then our linear mass density mu, which is our inertia that prevents the string to return to its equilibrium. Example of the calculating wave on the speed. One end of a 2-kilogram rope is tied to a support at the top of mine shaft, which is 80 meter deep. So the rope is stretched out by a 20-kilogram box of rocks attached at the bottom. So the question A, the geologist at the bottom of the shaft signals to a colleague at the top by jerking the rope sideways. Now, what is the speed of the transverse wave on the rope? So for question B, if a point on the rope is a transverse in simple harmonic motion with frequency 2 Hz, how many cycles of the wave are there in the rope's length? So this is the illustration. So this is supposedly the mountain, and we have the rope here has the mass of 2 kilogram, and then we have the sample or this stone which is attached to the rope, which has the mass of 20 kilogram, and then the height of the or the depth of the hole is equal to 80 meter. So for question A, so our target variable is the wave speed. So using the dynamic relationship of V is equal to square root of F as our tension force divided by mu, which is the linear mass density or mass per unit length. In order to find the tension force, we have F is equal to mass of the rope due to the box. We have 20 kilogram times its gravity. So 9.8 meter per second squared. Do the math. We have to multiply this one. So we get the value of 196 Newton. We already have the value of tension force. Now, let's proceed to find the value of our mu, which is the mass per unit length. From the formula of mu is equal to mass divided by its length. So, given the mass of the rope, which is 2 kilogram, divided by its length, which is 80 meter, so it is just equivalent to the depth of the bottom. We have 0.025 kilogram per meter. Now, since we already have the value of the tension force and the linear mass density, let us now substitute the values. V is equal to square root of our tension force, which is 196 Newton, divided by the mu, which is 0.025 kilogram per meter. Do the math. We get the value, which is 88.5 meter per second. So this is now the wave speed of the rope. Now, for question B, we need to find the wavelength using equation V is equal to lambda times its frequency. In order to find the wavelength that will fit in 80 meter deep. So, wavelength is equal to wave speed over its frequency. So, since we already have the value of wave speed in the question A, and then we already given by the frequency, which is 2 Hz, just substitute the value. We have 88.5 meter per second divided by its frequency, which is 2 Hz or 2 per second. Do the math. We have 44.3 meter. So in order to get the wavelength of the 80 meter, so we just have to divide the wavelength we've got. So 80 meter divided by 44.3 meter, we have 1.81 wavelengths. That is per cycle. Every wave motion has energy associated with it. So the energy we receive from sunlight and the destructive effects of ocean surf and the earthquake bears this out. As the wave propagates, each portion of the medium exerts a force and does work on the adjoining portion. In this way, a wave can transport energy from one region to another. Now, let's take a look on this transverse wave on the string. How this energy transfer. So, picture wave here travels from left to right on a string, and consider a particle A, which in point A, the string to the left of the point A, so this one, exert a force on the string. So this is the force on the string. So to the right of it, and vice versa. Figure B, string to the left of the point A has been removed, and the force it exerts at A is represented by the component Fy and F. Note that Fy over F is equal to the negative slope of the string. It's also given partial derivative of y with respect to x. Put together, so we have Fy as a function of x and t is equal to negative F partial derivative of y as a function of x and t with respect to x. When a point A moves in y direction, the force Fy, so this Fy does work on this point A, and therefore transfer energy into the part of the string to the right. The corresponding power, or the rate of doing work at point A, so is the transverse force of F as a function of Fy as a function of x and t. So at A, at a time, the transverse velocity F, or transverse velocity Vy. So this is our transverse force, so Fy as a function of x and t, and our transverse velocity, which is Vy as a function of x and t. Our power, so this will be the equation in getting the power of this point A. So the rate of doing work, so P is as a function of x and t is equal to Fy as a function of x and t times the Vy, a transverse velocity, as a function of x and t. Since our Fy as a function of x and t is negative f times partial derivative of y as a function of x and t with respect to x, so substitute, and then our Vy, this power is the instantaneous rate at which energy is transferred along the string. So its value depends on x. The value power is depend on x and t. Note that energy is being transferred only at point where the string has non-zero slope, where the string has a non-zero velocity. So for a sinusoidal wave given by function y as a function of x and t is equal to a cosine kx minus omega t, in order to get the power, so first we have to derive with respect to x. So this function with respect to x, so we have negative k a sine kx minus omega t, and then we have to derive the function with respect to t. So we have a sine kx minus omega t. We can have now the power, since the power formula is equal to p as a function of x and t is equal to negative f times partial derivative of y as a function of x and t with respect to x times partial derivative of y as a function of x and t with respect to t. So putting together, so we have negative f, so times negative k, so we have positive f, and then this, so k omega, so a times a, so we have a squared, so sine times sine, sine squared, and kx minus omega t. So this will be the power for a sinusoidal wave. Using the relationship omega is equal to wavelength times its wave number, and the wave speed squared is equal to F, or the tension force, divided by mu, which is the linear mass or the mass per unit length. So we have, so substitute the value of K and F, and then the K. P as a function of x and t is equal to square root of mu and times F times omega squared, a squared, sine squared, and then the kx minus wt, or the omega t. So remember that sine squared must not be equal to negative, but it could be either positive or negative. So it positive simply means that there is a energy transfer, while when it is zero, it means that no energy transfer. So energy is never transferred in the direction opposite to the direction of the wave. There is no energy transfer when it is opposite. When the wave traveling from left to right, and there is no energy traveled from right to left. Now, maximum value of an instantaneous power occurs when sine squared has the unity, or has the value unity, which is P max is equal to square root of mu and F times omega squared and a squared. In order also to get the power average, or average power, So we just have to get the 1/2 of the P max or our power in maximum. As you can see in this illustration, average rate of the energy transfer is proportional to the square of the amplitude and square of the frequency. In mechanical wave, the rate of energy transfer will be quadruple if we double the frequency with the same amplitude, and or if we double the amplitude with the same frequency. Now let's proceed to the wave intensity. Waves on string carries energy in just one dimension, unlike the other types of waves which is in 3 dimension. So in 3 dimension, we define intensity as the average rate at which energy is transported by the wave, which is our power, per unit area across a surface perpendicular to the propagation. So we have intensity is equal to power divided by its area. So we measure intensity as watts or W over or per square meter. If the waves are spread out equally in all directions, so from a source, the intensity at the distance r is inversely proportional to r squared. This follows the energy conservation. So if the power output, which is P, or the I, or the average intensity on R's radius, and its surface area, which is 4 pi r squared, so we can get the equation as I is equal to P divided by its surface area. If there is no energy absorbed between the pairs, so P must be equal from I1 and its I2. Proportionality, which is I1 is inversely proportional to I2, is equal to R2 squared proportional to R1 squared. So this is what we call the inverse square law of intensity. Now the greater the distance from a wave source, the greater the area over which the wave power is distributed, and the smaller the intensity. Now we have here the example of power in the wave. In the example of wave on the clothesline, the previous example, the question is, at what maximum rate does Eva put energy into the clothesline? That is, what is her maximum instantaneous power? We have given the linear mass density of the clothesline is equal to 0.250 kg per meter. And Eva apply a tension force which is equivalent to 36 Newton. And B, the question is, what is her average power? And then, as Eva tires, the amplitude decreases. So, what is the average power when the amplitude is equal to 7.50 millimeter? Now, our target in the question A is to find the instantaneous power. So, we have to use the formula, which is P max is equal to square root of mu and F times omega squared and A squared. Given the value of mu, so substitute all the values. So we have the value of mu, which is equal to 0.250 kilogram per meter, and our F or our tension is equal to 36 Newton, and we have our angular frequency, which is equal to 4 pi rad per second squared, and then we have the amplitude given, we converted it into meters, so we have 0.075 meter quantity squared. Do the math, we arrive this answer 2.66 watts. So remember the unit of the power is watts. And in question B and C, we are both going to get the average power. For B, we use the average power is equal to 1/2 of our maximum power. We have 1/2, substitute our, we get already the maximum power, 2.66 watts. We have this 1.33 watts. For C, given the amplitude, since the amplitude are proportional to the power, so and the value so the value 7.50 is the so the new amplitude is 1/10 of the value we used. So 1/10 the value of we use the amplitude 0.75. Now so it is 1/10 the value we used in the solution A. So substitute the value, so the same, it is 1/2 P max, but at this time, so we use the average, the maximum, we use the average or the average power in getting the average power of the new amplitude. So 1/10 quantity squared times our average power, so we have 0.0133 watts, or convert it into milliwatts, so we have 13.3 milliwatts. So this is the average power where our amplitude is about 7.50. This equation, square root of mu f times omega squared and a squared, shows that P max occurs when sine squared times kx minus wt is equal to 1. So, at any point of x, this happens twice per period of the wave, and once with the sine function is equal to positive 1 or negative 1. And our minimum instantaneous power is 0, and this occurs when sine squared kx minus omega t is equal to 0. This happens twice per period. Now, let's proceed on the wave interference, boundary condition, and superposition. So, when wave strikes the boundary of its medium, all or part of the wave is reflected. So, this is what we call the reflected wave. Now, when you flip the end of a rope or string, whose far end is tied to a rigid support, a pulse travels the length of the rope and is reflected back to you. So in both cases, the initial and reflected waves overlap in the same region of the medium. So this overlapping of the wave is what we call the interference. Interference refers to what happens when two or more waves pass through the same region at the same time. The simple example here, which is in A, we have the condition that where the wave reflects from the fixed end. So if the end is fastened to a rigid support, the arriving wave exerts a force on the support, the reaction to this force exerted by the support kicks back on the string, and that it resulted or reflected pulse. This pulse moves opposite on the initial pulse, and the displacement is also opposite. So other situation is that free end, one that is perfectly free to move. So in the direction perpendicular to the string or the length of the string. So spring may tied on the light ring that slides on the friction rod. So ring and rod maintains its tension but exert no transverse force. When the waves arrives at this free end, the ring slides along the rod. The ring reaches now its maximum displacement, and both it and the string come momentarily at rest. The string is stretched, giving increased tension, so the free end of the string is pulled back down. And again, a reflected pulse is produced. Direction of this pulse is the same with the initial pulse. This moment there is a reflex but without inverting the wave. So we learned that interference or the overlapping of the waves, which in general term refers to what happens when the two waves travels or pass through with the same region at the same time. So now let's have what we call the boundary condition. So boundary condition is the conditions at the end of the string. It could be such as a rigid support or the complete absence of the transverse force. So the formation of the reflected pulse is similar to the overlapping of the two waves. So figure here shows that two poles with the same shape, one is inverted with respect to the other, travels in the opposite direction. So as the poles overlap, and pass each other, the total displacement of the string is the algebraic sum of the displacement at point where the individual pulses arrives. So because these two pulses have the same shape, the total displacement at point O, so 0 at all times. Of the left of the string would be the same if we cut here at the point O. So throw away the right side. So this will be the remaining. Combining these two, the total displacement at O is always 0. Previously, we have talked the reflection of the wave on the string. Now let's look at the happens of the sinusoidal wave when it is reflected by a fix on a string. So we'll again approach the problem by conducting the superposition of two waves, and now this one represented the initial wave and the other is the reflected wave. Figure A to D shows that the string is fixed at the left end. Then its right end is moved up and down in simple harmonic motion. So to produce a wave that travels to the left, so the wave reflected from the fixed end travels to the right. So the resulting motion when the two waves combined is no longer like two waves traveling in opposite direction. So the string appears to be subdivided into a number of segments. So just like this one. So as shows at the time exposure, the figure A, B, C, and D. Here, instead, the wave pattern remains in the same position along the string and its amplitude fluctuates. So these are the particular waves called nodes. This that never moves at all. Midway of the nodes are point called antinodes. So the midway of these nodes is what we called here the antinodes or antinodes, where amplitude of motion is greatest. Diba? As you can see, the amplitude here is the maximum positive and maximum negative. Because the wave pattern doesn't appear to be moving in either direction, so doing this along the string, it is called the standing wave. So this is what we call the standing wave since it doesn't appear to be moving. Ba? So to emphasize wave that does not move along the string, it is called traveling wave. So as the example previously in the wave of the string, which is, you can see that it is moving, so that's what we call the traveling waves. From this illustration, so you cannot see that it is moving from what direction, so it is just we call the standing wave. Also this one, so this is what we call the antinodes, the nodes, antinodes, nodes, antinodes, nodes. In an instant, the wave coincide, so they add to give maximum string displacement or displacement. So at the instant, two waves are exactly out of phase, so the total waves is 0. Now the resultant of the wave or the resultant of any displacement is always 0 at the nodes, since from here nibalik ra siya. In every nodes is 0 since niagi siya dira and then nibalik ra po siya diha. So there is no displacement when you came back where you started. The displacement of the waves is always equal and opposite, so therefore we can cancel it out. So this cancellation is what we call the destructive interference. While on every antinodes, so the displacement of the two waves are always identical, giving a large resultant displacement. So in antinodes, we have what we call the constructive interference. So the waves are add up, while on the nodes are subtract or cancelled out. Constructive interference. As you can see, a successive nodes or antinodes is always 1/2 of wavelength. Now we can derive the wave equation for standing wave by adding the wave function y sub 1 x as a function of x and t, and y sub 2 as a function of x and t. So this is for two waves which is equal in amplitude, wavelength, and period. We can have that this y sub 1 as a function of x and time, this represent the incoming wave or our incident wave, while this y sub 2 as a function of x and t is our reflected wave. So this is the incident wave and this is the reflected wave, which traveling to x is equal to 0. Wave reflected from fixed end if a string is inverted. So the negative sign, which is we have y as a function y1 as a function x and time is equal to negative a cosine kx omega t. This is for the incident wave traveling to the left. So direction of this wave is traveling to the left. That is why we have the negative sign. And we have y sub 2 sa function of x and t is equal to a cosine kx minus omega t. So this is for the reflected wave which is traveling to the right. So we have the positive sign. So note that change of sign corresponds to a shift in phase. So it could be from 180 to pi. So 180 to or pi radians. 180 or pi radians. So at x is equal to 0, so motion from the reflected wave is this one, a cos kx minus omega t. So which we can, at x is equal to 0, so we have the reflected wave which is, if x is equal to 0, so we have a cosine omega t. So substituting that our x is equal to 0, which we can rewrite as a cosine. We can write this at a cosine omega t plus pi. So this is wave function of a standing wave if the sum of the sinusoidal wave function y sub 1 y, we can have this y as a function of x and t is equal to y sub 1 as a function of x and t plus y sub 2 as a function of x and t. We have so we have here the cosine negative, diba? Since initial wave is negative, so we have negative cosine kx minus omega t plus cosine kx minus omega t. So we can have to get this is now the equation of the standing wave on the string. Now from our previous equation, which is y as a function of x and time is equal to 8 times negative cosine kx minus omega t plus cosine kx minus omega t. So we can rewrite the cosine function according to the cosine identities. We all know that cosine a plus or minus b is just equal to cosine a times cosine b plus or minus sine a and sine b. So do the math. So replace the value of our cosine. So we have the 2a sine kx times the sine omega t. Or we can rewrite it in a simple way. So we have the y as a function of x and t is equal to amplitude of a standing wave times sine kx times sine omega t. So remember that the amplitude of a standing wave is equal to the or twice of the amplitude. In order to get the position of the nodes, we must get the value of kx is equal to 0. And we can get the value of k, which is 2 pi over lambda. So remember that nodes can be found where our x is equal to 0. Remember that standing wave, unlike a traveling wave, does not transfer energy from one end to another. So the two waves that form it would be individually carry the equal amounts of power, which is in opposite directions. There is a local flow of energy from each node to the adjacent antinodes and back, but the average rate of the energy transfer is zero at every point. If you evaluate the wave power given by the energy transfer, so you can use the wave equation. Now, let's proceed to the normal modes of the string. So, when we describe standing waves on the string rigidly held at one end, as we discussed previously, we made no assumptions about the length of the string, or about what was happening at the other end. So, let's now consider the string which are held in both ends. So, such strings are found in many musical instruments such as piano, guitar, violins, and any other. So, when a guitar string is plucked, a wave is produced in the string. So, this wave is reflected and reflected from the ends of the string. So, to understand these properties of standing wave on a string, let's first examine what happens when we set up a sinusoidal wave both on such string. As we discussed previously, it produces a standing wave, which has the adjacent node has its length, which is 1/2 lambda, or 1/2 of the wavelength. So apart from each other, we must have the length, which is lambda over 2, or 2 lambda over 2, or 1 lambda, or 3 lambda over 2, or 1 and 1/2 wavelength. So this is the series. So each node has the half of the wavelength. Now, this is for the string which is fixed at both ends. So, we can rewrite the formula into length is equal to n times lambda over 2, which our n must be equal to 1, 2, 3, and so on. This counting number. When you get the lambda, you can rewrite this equation as lambda sub n is equal to 2L over n, which also our n must be 1 or 2 or 3, and so on. So the same, it is still in the string fixed at both ends. Now, corresponding to the series of possible standing wavelength lambda n is a series of possible standing wave. Frequency Fn, which is related to its corresponding wavelength, such as we can say that frequency sub n is equal to V over lambda sub n. This lambda n is just equivalent to L. For our frequency 1 is equal to V over 2L, which is F sub 1 is our fundamental frequency, which this fundamental frequency hold the largest wavelength. We can also get the frequency 2V over 2L, our frequency 3V over 2L, and so on. We can write it in general form, so Fn is just equal to n times V over 2L. So where our n must be equal to 1, 2, 3, and so on. These frequencies, F1, F2, this is what we call the harmonics. When it is in series, so we can say that it is harmonic series. Now, musicians sometimes called F2, F3, and so on as overtone. So F2 is the second harmonic, and then it is first overtone. And F3, third harmonic, which is second overtone, and then the other must follow. Now, for a string with fixed end, which is x is equal to 0 and x must be equal to L, which is our length, the wave function y as a function of x and t of the end standing wave is given this equation for a standing wave. This satisfies the condition, which is there is a node at x is equal to 0. Our angular frequency, which is angular or omega sub n is equal to 2 pi f sub n, or we can translate our k as k sub n, or our value of k, which is 2 pi over lambda sub n. We can rewrite the equation as y sub n as a function of x and t is equal to a standing wave amplitude sine k sub n times x multiplied by sine omega sub n times time. Now, we have what we call the normal mode. So, this is the oscillation of the system, which is a motion in which all particles move sinusoidally with the same frequency. As we have seen, the fundamental frequency of a vibrating string, so we have f sub 1 is equal to v over 2L, the speed v, which is equal to the square root of f, which is our tension force, divided by its mu, which is the mass linear density or the mass per unit length. We can combine this expression into f sub 1 is just equal to 1 over 2L times square root of f over mu. We must remember that F1 or a frequency depends on the properties of a string. So when you increase the tension of the string, it also increases your wave speed and also your frequency. And lastly, increasing your mass per unit length will decrease your wave speed and also your frequency.